It did work. Oh, hooray, hooray. I could not be happier. Okay, so anyway, my recording works. So now I've got this nice field line diagram. I want to talk about how this leads into Gauss's law. So first of all, let me just save this file real fast, make sure blah, 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 fine, untitled, PNG, good enough. Okay, so I want to talk about how this gets into Gauss's law. Now, remember when we did this, we picked that we were going to draw 4 lines for every nanocoulomb of charge. So this guy, for example, has 3 nanocoulombs, positive 3, so he has 4 lines coming out. I do need to sort of make it clear. Let me get the eraser and see if I can fix this. These little things here are just little, my errors. They're not actual arrows, okay? So hopefully now everything looks reasonably sane. 4 pointing in here, or sorry, 8 pointing in here, 4 pointing in here, 4 pointing out here, and then the ones going up to infinity. And we got 4 lines for every nanocoulomb of charge in these things. Now, what I'm going to tell you, and this is probably going to seem kind of obvious once you think about it, is that I can take and I could draw any curve, any closed curve on this, and go, let's say I do this as my closed curve. And what I'm going to tell you is that the number of lines that cross that curve, I can count the number of lines that cross that curve, and they will be, that will tell me how much charge is totally contained inside the curve. So I'm going to say here is, let me go back to this color, and say number of, why do I have a different width now? This is strange. Okay, number of lines crossing curve. You know what, actually I'm just going to, lines crossing a curve, okay, divided by 4 equals the enclosed charge. So I'm going to QENC to mean the enclosed charge inside the curve. So the number of lines crossing the curve divided by 4 equals the enclosing charge. So here we have how many lines cross this thing going in here? 1, 2, 3. This guy comes in and then out, so I'm not going to count him. I'm going to count as like 1 coming in and then 1 leaving. So this is a net 0 lines crossing, if you can see that. So that's 0 here, then 4, 5, 6, 7, 8. This is our first one, remember? So there's, again, 1, 2, 3. This one doesn't count. 4, 5, 6, 7, 8. And we have 8 coming in. So for this green one, I'm going to say 8 lines in divided by 4 lines per nanocoulomb gives us -2 nanocoulombs, which is the enclosed charge. Why do I say -2? Well, so you could probably guess ahead and say that whether they're coming in or out matters, okay? So what I'm going to say is 8 lines in is like a -8 lines, because there are 8 lines coming in. So really what I'm going to do actually is erase this, and instead of calling it 8 lines in, I'm going to call it -8 lines crossing this thing. So -8 lines divided by 4 lines per nanocoulomb gives us -2 nanocoulombs. Okay? Now, just to see if we've got this idea, I'm going to draw another one. Let's see if I can get a thicker marker. I don't know. Let's draw one around this guy. Let's draw around this guy in blue. How many lines do we have crossing this guy? 1. This is going out, right? 1 out, 2 out, 3 out, 4 out. So the total for this guy, I'm going to call outs positive and ins negative. So this guy is +4 lines divided by 4 lines per nanocoulomb, and that gives us +1 nanocoulomb enclosed. And look, that's what we have, right? Okay, so let me go out and make one little addendum to this whole rule. The number of lines crossing divided by 4 equals Q enclosed. So probably more appropriate to say number of lines going out divided by 4 equals Q enclosed. Okay, so I'm just taking this ratio here and dividing it by the number of lines that cross any given curve I draw. Let me draw another closed curve. Let me do this one in red, And this time I'm going to be a little sneaky, and instead of doing just one of these charges, I'm going to do both this -1 here and the 3, okay? So I'm going to draw a curve that goes around these guys. Hold on, I actually want to enclose this guy. Okay, so now how many cross this red line? And now I'm just going to start counting. Lines going out are going to be positive. Lines going in are going to be negative. So this guy here, and in fact, I think what I'll do is I'll mark these, if I'm not cluttering this up too much, I'll mark it's positive or negative. Okay, so this one here is positive. This one here is going out, that's positive. Positive, 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 positive. This thing here is positive, right? But then when we come back to this thing, it's negative. So actually, this is going to cancel out here, you can see, okay? Then here, this is negative, because it's coming in. This line's coming in negative, okay? This one doesn't quite touch it, so that's okay. This is positive because it's going out, positive it's going out, and positive it's going out. So how many do we have total? Let's see. We have, for the red, we have 1, 2, 3, 4. So I'm going to start with this guy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, -1 now down to 10, 9, 8. And then we're back here. So for the red, we have 8 lines out, a net 8 lines going out. And actually, sorry, I shouldn't write out. I should write that as +8, right? So +8 lines going out divided by 4 lines per nanocoulomb. And that means we have a net charge of +2 nanocoulombs inside. And sure enough, +3 -1. So that works. So this probably seems, on one level, it's kind of obvious, right? But this leads us into Gauss's law, which is a very powerful idea that lets us compute electric fields in a lot of places. So imagine now, of course, this is a two-dimensional drawing, and in real life, you've got three-dimensional field lines. So in real life, you'd have to imagine you're doing this with a closed surface that encloses these guys, and then the field lines punch through the surface, and you count the number of field lines that punch through that surface. So we're going to take this idea and go forward with it in the next video I do.